So, there's a topic in math that I've been learning about recently, and I didn't really properly appreciate, I think, what this topic actually was until I came across this one really elegant proof. So, I'm going to share the proof with you and hope you'll also find it really elegant. The topic in question is a field of math called topology. Now, topology has been best described as like the study of spaces and how they morph onto other spaces. I'm not talking about geometry, so this isn't about shapes. Topology isn't concerned with things like, volumes or side lengths, things like this that we care about deeply when we do geometry. You might have heard at some point this fact about how, topologically speaking, a donut is the same as a coffee mug. This is a very famous sort of thing to say in math. The idea is that a coffee mug has one hole in the handle, and a donut has one hole. So if I took a donut and it was malleable, I couldn't rip it or tear it, but I could stretch the material. I could reform it into a coffee mug. So one way you can think about it is that it's the study of like how many holes something has, but that doesn't really get to the heart of what it is, and I'm gonna aim to convince you of that, I suppose, in this video. A bit more terminology we need to talk about. There's something called a mobius strip, and you might know what a mobius strip is. I think people would have done this in high school at some point, but the idea is that if I have a bit of paper, and we're going to do this visually, if I connected it at its ends like this, I just created a loop, right? This is sort of like a hole. I mean, this is again my coffee mug shape, right? It's an object with one hole in it. I could also create a half twist before I connect it and end up with something like this. This is called a mobius strip. So a mobius strip is one continuous space that has this half twist and it wraps around. Interestingly, a mobius strip doesn't really have an outside or an inside. It's only got one continuous face and it's only got one continuous edge. So you can imagine if you were an ant living on the surface of this mobius strip and you walked around it, you could keep walking and end up on the inside of it and then come back out to the outside of it. So there's no inside and outside like there was on my regular loop, where if an ant starts here, he's never going to be able to get underneath himself. The same is true of the edge of the mobius strip. So if I take this edge and follow it all the way around, I'm going to end up back where I started. I'm going to bring an image of a mobius strip up on screen. Hopefully this will upload. I've just taken something from Google Images because it's hard to see, especially with topology. It's hard to see these shapes it's hard to appreciate what they are unless you can look at them. So let me just paste my shape. Copy. Paste. Here it is. Cool. Mobius strip is this shape here. Now, what's this shape? This monstrosity? This is called a Klein bottle. Klein was the mathematician who studied them. And a Klein bottle is interestingly what you get when you glue two mobius strips together. And this is again one of those facts that I'm not going to spend time proving, but you're just going to have to accept for the sake of this proof. People have proven it. A Klein bottle is a four-dimensional shape. And then you might be asking, well, how can it exist in three dimensions? It's because of this point here that passes through itself. A perfectly ideal Klein bottle wouldn't have a point of self-intersection. But if you're going to ground the Klein bottle in three dimensions, you're going to have that point of self-intersection. So you can think of it as if, like, in the four-dimensional version, this intersection doesn't have to happen because that tube can go into the fourth dimension a little bit and then come back in, and then it didn't have to actually pierce the side of the bottle here. Here's a image that somebody created to kind of show this idea. So this thing in the middle here is a Klein bottle, and these are the left and the right half of the climb bottle, and you can sort of see how they're both mobius strips. This is the same shape as a mobius strip, just bent around a little bit. Anyway, with those facts out of the way, that's all we really have to worry about. So I'm actually gonna get rid of them for now, and we'll just come back to them when we need them. But yeah, there's a mobius strip and a climb bottle, and a climb bottle, if it's in 3 dimensions, has to intersect itself. Those are the key facts we need to know about. Okay, let's get into the proof. The proof says that in any closed shape like this, a blob, let's say, there exist 4 points on the blob where if I connect them up, I get a perfect rectangle. Now here, this isn't really a perfect rectangle, and I'm not saying it's true for any set of 4 points, I'm just saying that there exist 4 points such that I can draw this rectangle. This is true, and I'm going to aim to prove it. Now, it's obviously true for things like circles. In fact, there's going to be an infinite amount of ways that I can draw it. I could pick these. I could pick these 4 points here, and that's my rectangle, right? It's also going to be very obviously true on a shape like an ellipse, because on the ellipse, again, I can just draw my rectangle like this. But it's going to be less obviously true on shapes like this. This big mess here. So let's start the proof. Well, instead of thinking of it as 4 separate points, let's kind of think of it as 2 pairs of points. And those points are going to be the 2 ones that are adjacent to each other. So let's say, for the sake of argument, we label this P1, P2, P3, and P4. Now, what are some things that we know about this shape? Well, because it forms a rectangle, we know that the distance between P1 and P3 has to equal the distance between P2 and P4. So let me try and write that down mathematically. We're going to say, let's say D is a function that takes in 2 points and outputs their distance. We're saying that D of P1, P3 is the same thing as D of P2, P4. Well, how is this helpful? Well, it's not obvious why it's helpful. So I'm going to just get to the next step of the proof, and hopefully it'll become apparent soon. Imagine if I took this shape, and instead of having it on my screen, I had it on a flat bit of paper. And I added some sort of Y dimension, or I guess Z dimension, if you don't play Minecraft. Bring it out of the page. So I'm going to do that. I'm not very good at these graphics things, but imagine my shape again that I've drawn. But this time, it only exists on a sheet of paper. So let me try and redraw my shape. I've printed it out and I've put it on the floor. And now let me consider any pair of points on this shape, like these two. And let me think about the distance between them. Here's what I'm going to do. I'm going to go right in between those 2 points and and then raise it up, whatever the distance between those 2 points are. And I'm going to do that for every possible pair of points on my shape. So for an example, this point and this point, this is a pair of points. So again, I'm going to form a warp between them. And in the middle, I'm going to erect it by its distance. So this might come up to here. Eventually what you're going to get is this really wonky shape that's going to go at the very top of my space. Right? What the hell is this thing? We have no idea what it is. We know it's going to be some kind of continuous space, because as I nudge 2 points, their distances are going to nudge by a little bit. So the space is going to be continuous, but we don't really know anything about it. But here's what we do know. if this paradigm is going to happen, that there are 4 points that create a rectangle, that means that there are 2 different pairs of points here on my shape that have the same midpoint, like this point here, and the same distance. Which means for my big shape, that point is going to be erected by the same distance twice, which means that it's somewhere on top of my shape, there's going to be a point of self-intersection. Self-intersection just means that the shape is going to cross through itself at least one point. Now, hopefully you can see that if this shape crosses through itself at any point, that means that there are 2 pairs of points on my shape that have the same midpoint and are the same distance apart, which is actually what it means to be a rectangle. So I've reworded the problem completely, but these 2 problems are isomorphic. They're describing the same thing. If this shape can exist, then this shape must have a point of self-intersection. Alright, let's zoom out a little bit and keep that in mind. This space, what it represents is picking 2 points on, let's say, a ring, in every way that you can pick 2 points on a ring. So let's think about a ring. And what does it mean to pick 2 points on a ring? Like, say, point here and point here. Let's say that this is side 0, 0 point on the ring, this is the 1 point of the ring. If I want to represent 2 points on a ring, I could create some kind of grid here, where my first point is going to be on this side, and my second point is going to be on this side. So here, my first point was about 1/3 of the way in, and my second point was far closer to 1, it was about here. So this X here represents what it means to pick 2 points on a ring. Now this is fine, but we do have one more problem, and that problem is that 0 and 1 wrap around. Basically what it means is that if my point X travels high up enough in this direction, it needs to come back in from the bottom, which is basically going to be the same thing as my point here moving across this arbitrary seam that I've created. The same thing is true if we're going too far in this direction, it'll come in this direction, and again, vice versa, right? Too far down or too far to the left. This is a shape that wraps around. Now, if it's a shape that wraps around, we can think of it as this sheet of paper, where this side wraps around to this side, and this side wraps around to this side. Now, if that's true, let's just bend the paper to reflect that. Now what I end up with is something like this, a cylinder. Basically, I've just taken the left side and the right side and glued them together. But now, I need to do the same thing for the top and the bottom and wrap those around and have them touch each other here. Now, it's going to be hard to do this with a sheet of paper, but what that's going to create is a donut or a torus. Imagine a really long cylinder and then be gluing one end of the cylinder to the other. I've created a donut shape. So this space can be thought of as a donut, or traveling around the surface of a donut. You can take that and play with it and then think, well, if that space is a donut, then this space has to be a donut. But that doesn't give me any information about this point of self-intersection. A donut doesn't necessarily have a point of self-intersection, so I haven't really gotten anywhere. The reason is because it's not a donut, and there's one key element that we're missing. Let me redraw again. So I'm going to do the same principle, where I'm going to have my square. This represents the states of P1, this represents the states of P2, and again we have this wrapping around idea where this side wraps to this side, and this side wraps to this side. But we've got a problem, and that problem is we're counting the same states twice. Let's say on my ring, I've picked this point and this point. Well, if that bottom point is P1, and that other point is P2, I'm going to end up with a point here, right? But if this bottom point is P2 and the other point is P1, I'm going to end up with a point here. Essentially, my problem is that every possible state of picking 2 points on this ring is being counted twice. Once here and once here. And I shouldn't be counting them twice, because these labelings are completely arbitrary. It shouldn't matter. So basically what it means is that across this line of symmetry, this red line of symmetry, I need to kind of take this corner and fold it over to this corner, flattening it, to flatten it. So let's just do that. And I'm going to have to make myself some room here. I'm going to do it a bit more small. Let's flatten this shape. So I'll leave the red line in. And remember, I have to keep my property here where this connects to here. And this side connects to here. Alright, cool. So now this is my shape. With an edge line here, this red edge. Now, can we imagine what it would be like to fold this in real life? Probably not. It's going to be really, really difficult. And the reason is because I can't really take this side and bend it to make it point out this way. So let's add some more cuts. Let's make a cut here. And remember, I'm going to have to glue this back together again. So I'm going to put a green arrow here. Now what I'm left with is two triangles. One that looks like this, and the other that looks like this. Now what I'm going to try and do is glue my two triangles together, but I'm going to start with the black arrows. Now these black arrows are going to need to be twisted 180 degrees. I'm going to take this triangle here and pick it up and flip it in real life, which in topology I'm allowed to do. And when I glue them back together again, along these black sides, what I end up with is something like this. So you might be thinking, well, okay, it's not a donut, it's a ring. Because now I can take the square and wrap it around, and I get a ring shape, or I guess a better way of putting it would be a cylinder. But I get a cylinder. But it's not a cylinder, and the reason is because this arrow here needs to chase this arrow, which is on the left side, not the right side. Which means that I'm going to have to do a half twist when I do my gluing around motion. So I take my space, and instead of just gluing them together like this, I do a half twist before I connect them. This is why I brought up mobius strips. This shape here is a mobius strip. Alright. Which means that because this shape is the exact same as my big yellow monstrosity that I've drawn, these are both mobius strips. So this yellow shape is a mobius strip. So let's keep that in mind. We can represent it as a mobius strip. I'm going to get rid of all these. Now, because it's a mobius strip, how does that help me prove that it has a point of self-intersection? Well, it doesn't really, because a mobius strip doesn't necessarily have a point of self-intersection. But you know what it does? A Klein bottle. This thing I've circled in red. The Klein bottle has at least one point of self-intersection, and it's what you get when you glue two mobius strips together at their one edge. So let's take this yellow shape and let's reflect it and put a negative yellow shape underneath it. I've just taken a shape and I've doubled it and put it underneath, and I've glued them together. I've glued the shapes together at its one big edge. So now if I do the same thing for a mobius strip, I get a Klein bottle. So this new big yellow shape that I've made is a Klein bottle. Am I spelling Klein properly? What have I done? E-I-N, yeah. There's a Klein bottle. And a Klein bottle has a point of self-intersection. Therefore, this has a point of self-intersection, and therefore there do exist 4 points on my shape that form a rectangle. And that actually completes the proof. That's a really, really interesting proof. I might not have explained it very well. It's very, very complicated. I had to read a lot of topology to understand some of these ideas. But yeah, so topology isn't just about donuts and holes. It's about spaces and how spaces can map onto each other. We didn't know anything about this yellow shape, but yet we wanted to study it. But we knew that it was derived from picking 2 points on a ring, and that we can represent as a space. And all we did in this problem is that we took that space and we morphed it around without cutting it up or doing anything like this. Or, well, we did cut it up, but we glued it back together where we cut it, so that's fine. And we ended up figuring out that that shape is a mobius strip. And this sort of stuff comes up in math all the time. And I guess I didn't realize that until this problem. But yeah, so now you can go tell your friends that on any shape you can draw like this, there's going to be 4 points to draw a rectangle. Interestingly, we can actually strengthen this proof to say not just a rectangle but a cube. Sorry, not a cube, a square I should say, like a rectangle but they're all the same length. And that is a lot harder to prove. And I think it might involve some 4-dimensional stuff, whereas this was all just 3-dimensional. But yeah, anyway, that's the end of the proof, and hope you followed along, and thank you for watching. Cheers.